Our next speaker is Christina Kelly from LECO. Christina will talk about characterization and quantitative hydrocarbon group type analysis of plastic-derived pyrolysis oils by GC-TOFMS/FID.
Thanks, Peter, and thank you to the organizers for giving me the chance to talk. Genesis has already done a really great introduction to pyrolysis oils, so I probably won't spend that much time talking about why they're important, because she did a great job covering all of that. I'm going to focus a little bit more on the different GC by GC instrumentation options. No surprise, being from LECO. So we'll talk about some of the GC by GC options we have, the group type analysis, which has already been pretty well covered in this afternoon's session, a little bit about how we've applied the tile-based statistics from our chromatograph tile software, as well as some heteroatomic species identification, which we can use with our high-resolution instrument. So you can see here an image of just plastic waste going through different pyrolysis reactions and creating product pyrolysis things. I forgot I had done all this animations, but basically I was given 6 pyrolysis oil samples, and unfortunately, unlike collaborations with universities where you know exactly where your samples come from and what they are, I was told, here are 6 samples, tell me about them. I was given a little bit of information later on after revealing some of the chromatograms I generated, that they came from different places along a process line at different dates. And so you can see the different coloration, it's all the same process, supposedly from the same feedstock, just at different points in the production line. And so whether it's a condenser line, or a product tank, a collection tank, or the knock tank at the bottom, you have kind of different fractions of what was collected. But there's shouldn't have been so much variation between those things at different points in the process. They were pretty surprised at the color variation, the viscosity problems they were getting, and some of the density measurements they were doing on these particular samples. So being in the apps lab at LECO, you have a lot of options to play with for what you want to do when you first get a bunch of samples. And we have our QuadJet SD option, our FID thermal modulated system. We have our Pegasus BT, which we've already seen a lot of data from our benchtop system, as well as our high resolution HRT40. I have a little space there because recently, and you've probably seen at this conference several years now, we've been working on this new reverse fill flush flow modulator, the Paradigm Shift. And this system allows us to do the simultaneous FID and MS. So it's a reveal full flush flow modulated system coupled to the BT. So you have all the benefits of the BT, but kind of the cheaper flow modulation option that allows us to also split to the FID and get even quantitation at the same time. And so won't spend too long on this. The BT40 is high performance mass spec. It's quantitative for calibrated components, has really fast acquisition rate that pairs perfectly with GC by GC, and it also has extremely high sensitivity, which is what allows us to do the splitting that we need to the FID. And so with a paradigm shift system, we have the full transfer of our analytes from the primary column to the secondary column. We have software things in place, and we can always talk more with me about it afterwards if you're interested in how we make sure that everything gets transferred from the primary column to the secondary column, that you're fully flushing your loop and getting your optimal separation that way, as well as the splitter, the shift that maintains a constant ratio between your MS and FID. And so it's really important you're adding a bunch of flow using a flow modulator, that you split off that flow to the FID. We're still able to see, because of the high sensitivity of the BT, what you need to for those trace level components, even in a matrix as complicated as fuel. So we've got simultaneous qualitative and quantitative information. So for everyone here who likes to look at chromatograms, I've got several pretty ones to look at. Choosing the GC by GC column set is often kind of the first step you've got to do when you're deciding how to do your analysis. And so here I've got 2 videos that I think should play for, oh, nope, okay, it's okay. It's all right, we got the picture, it's good enough for everyone here. But basically with your normal phase column setup or your reverse phase setup, you have choices to make depending on what classes of compounds you expect. And so often when you have lighter jet fuel range or even lighter diesel type things, using the reverse phase is really, really nice because you separate everything in those paraffin ranges, like Genesis was showing. Traditionally, with some of the heavier things, the normal phase is better. You get more separation in your aromatics. And so you can see here the different column phases I used, 1 MS to a 17 in the normal phase. For this kind of reverse phase, 17 and then a 5 in the second dimension. And one thing that I found really interesting, and Genesis showed a little bit of that in her pyrolysis oils, is that we have our This is showing my pointer here. Nope. The typical pattern that you see is almost reversed when you get to those isoparaffins up top. And so you can see they're kind of going in the opposite direction. Instead of our typical going downwards in that trend, you see much more coming out with the reverse phase separation, which gets lost in the normal phase. And so it's just kind of interesting to see, depending on which compounds you're interested in, your column choice makes a really big difference when you're drawing those group type separations. Janice was also talking about some of the difficulties she has with just an FID. And so with your MS, you can then map out the GC by GC space using those characteristic masses. So we've got our alkanes here with our alkane cycloparaffins. And I mean, this is a really great example, right? Drawing boundaries, which one would you rather draw if you had to draw the boxes around? I would say the reverse phase is much easier for these particular group types. But then as you get into the aromatics, you have your monocyclic aromatics, your dicyclic aromatics, and you can see there's again, some choices that have to be made, some trade-offs then for where you want your separation power to be. And so 2.5 rings, and you get to your tricyclic aromatics. Something to also keep in mind is with your reverse phase separations, you have a temperature limit most of the time, right? Your second dimension column can't go to as high of temperatures. And so you have to be aware that column bleed can interfere with quantitation then when you go to some of those higher ringed species. So with that in mind, I decided I wanted to focus on some of the PAHs. Those seemed interesting with the normal phase separation. And so we drew classifications around there and got the area percent values from the FID. One thing I wanted to point out is that the only way we're able to do this using the MS and the FID so well is that we have a new novel alignment algorithm that you see here. We've got the S1, the FID trace, and our alkane. When we normalize, you can see you've got exact alignment, and that looks like this all the way throughout the chromatogram for all of your major peaks. And so if I had plotted like 105, you can see that where that S1 trace, those smaller bumps would then line up perfectly as well. And so all those different groups that you have, if you have to draw a lot of those squiggle boundaries with classifications, you'll know that having that basically perfect alignment when you're splitting gives you a really, really easy way of transferring, the information from mass spec back to your FID. And so back to those 6 different samples that we had, we can kind of see the distribution of the PAHs. So pyro sample 2, visually you can see the differences, but it's easier when it's kind of broken up into those group classes. The naphthalenes are a high contributor there, which could be making a big difference in those physical properties. We then use chromatography to look at the statistical differences between the samples, and we've already seen a lot of examples of that, so I won't go through how tile works, but basically we were able to highlight some of those oxygenated that were interesting in these samples as well. So here we've got a diphenyl ether, and we're also able to see that there is a oxygen with the chlorine peak here that was of interest in one of the samples, but not in the rest. And so somewhere along the process, we were able to see in pyrolysis oil 6, only that final sample has that. So somewhere along the lines, there's contamination in their process as they go from different points of sampling. So that was interesting to point out. Just wanted to show also with tile the ability to compare the trends of multiple features. So if there was something that looked interesting in one of those oils, but we had 6 different classes, it could have been multiple points along the line, we're able to track that throughout the different samples and see where there actually are differences and what compounds we're picking up throughout the process. So when we had, if we look at sample 4, for example, it's a lot of peaks. We can use tile to break it down, but also we can do kind of basic filtering. So you do your data processing that picks out your peaks, and then we can filter and say, hey, anything that looks like it might have a sulfur compound, and they're just looking at library matches. It's a very quick and dirty way of zeroing in on things that might be of interest that might cloud up production lines, and especially along these processes as they look at sulfur and different catalysts that they're adding into the process to treat these pyro oils. It's a quick way to look at analytes of interest. But that's just on the BT. And of course, when you have an HRT and you can drive it and you have some time, it's always fun to pop a couple samples on. I was able to sneak in a couple of these at the end of a different sample submission and just play with them, play with them on the HRT and see what we were able to see. So with the HRT, we have the multi-mode source, so the ability to do EI, PCI, and negative CI all on the same instrument without making any hardware changes. Literally just tune it up for each one, turn on your reagent gas, which happens automatically with your method, and you're good to go. And so kind of the workflow that we have that I've shown for pyrolysis oils that we can do, that you can do on the BT, right? You can acquire your data, you can do your peak find, you can filter and classify your peaks, you can do classifications, you can identify specific peaks, a lot of power and the ability of things to do. But with the HRT, we also have the ability to create composite spectra and look at things like mass defect plots, calculating those mass formulas and getting accurate compound identification. And so with these mass defect plots and Binkley plots, we can zero in then on some things that might have slightly different elemental mass defects that might also be interesting. So just an example of two of the samples in EI, positive CI, negative CI mode. You can see there's that selectivity difference. EI basically ionizes everything. PCI gives us molecular ions, so you see a little bit less signal, but you're getting better, higher quality, higher mass information for your samples. And then with negative CI, it's a totally different trace. And those are species that you expect to be more electronegative. And so after playing around with this, you can see that there are a lot of amines in these samples, as well as double, triple, some of them even have 4 oxygens on some of these things that you don't otherwise see in the EI. It gets covered up with all the other signals, but with negative CI, they're highlighted. The same thing is true for your really heavier PAHs. You have all of those different rings. Those are ionizing well in negative CI mode. And so you see them even when they're at super low levels. They don't show up as really important in EI, but negative CI brings them out, and you're able to get a better idea of what the speciation is. Back to the mass defect plots that we had talked about. When we filter for things that contain nitrogen, we're able to do kind of a quick comparison and know right away, your sample 2 had more contribution from nitrogen-containing species, as well as sulfur. And so when we look down at the different types of sulfur peaks we can get, so these are all mass signals, right? We look back at, we can take specific mass signals from the mass defect plot them back onto our chromatogram to see if they correspond to any peaks, and then get identifications of what is contributing to this sulfur hit in your mass defect plots. And so kind of all of those different puzzle pieces together allow us to get better identifications of individual peaks. So you can get that speciated information, as well as kind of that bulk characterization they get just from like how big your blobs are on the mass defect plot or on your chromatogram. And you can see the high mass accuracies here give us good confidence in the formalized assignments that we have. This is just from the positive CI. Again, fewer signals when you have more molecular ions present. But you can also go back to the EI where we had the fragmentation information, compare it back to libraries, and then confirm the identification of any given species you have. So in this case, we had a benzothiophene. And I was curious, we have a whole row of those mass defect dots. If we plot them all, then highlight that entire row, plot it all back, do we see all those different isomers, the C0, C1, C2, C3, C4, all those benzothiophene isomers are all present in our GC-GC chromatogram as well. And when you look back at the EI, it tells us, we know where to look now based on the PCI data. Back on EI, we already have some of those properly identified. We can continue to add to our knowledge of the sample with even better proper identification of those peaks. So the combination of our high resolution and GC-GC resolves the mass split issue. You can't approach it just from an MS point of view. With GC-GC, it gives you a lot of information, but sometimes it can be really hard to sift through all those different peaks. And so having that accurate mass information and GC-GC together gives you a really great way to sift through all the different data that you're able to get and pinpoint the analytes of interest that you have. So with that, hope I was able to give you a very quick taste on the variety of the LECO GC-GC options that we have. You can get high quality data, quantitative and qualitative, sometimes at the same time. You get the group type, bulk composition, and the ability to interface with our data, the statistical analysis of the difference between samples using chromatograph tile, as well as any sort of detailed identification. So if you want to do a quick bulk characterization, you can do that in chromatograph. If you want to do very detailed investigative work, you can do that in chromatograph. All of that is covered, and we have solutions kind of from the easy FID way all the way through to the detailed high-resolution TOFMS. So thank you.